Alright, so we got about 40 seconds before the lecture starts. What we'll be doing today is, the first thing I'm going to do is to go over the lab from yesterday, because I do want to make sure that everybody understands the concepts that are involved in this lab. And then what we'll do next is to move on to a new module, which is actually the assembly language programming part of this class. So that's going to be what we'll be doing today. Because I think we're done with most of the instructions. There are very few instructions in this case for this processor. Alright, it is time to start. So I'm going to get started here by first going back to the lab from yesterday and go over the concepts. So I'm going to do a preview. So I'm going to answer the questions just as you would. Alright, so the first question is, the increment instruction increments the value of a register, but it doesn't affect the flags. This makes the instruction more useful because in many situations, the objective is simply to add one, but we don't want to change the flags. Using the opcode table or the assembler, find out the binary opcode of the following instruction. So you got two ways to do it. One way is to use the assembler. So that way is the easiest way, because you just type in increment C and find out what is the binary code corresponding to increment C. And then the other way is just to test whether you know how to assemble code by yourself. So we go to the opcode table, we look up increment, which is right here, and it is 1101, and then we have two instances of XX here. That's because XX is specified twice. So C is going to be 10, so we end up with 1010 as XXXX. So the entire bit pattern is going to be 1101 1010. Alright, so let's put that in. 1101 1010. That's for question number 1. And then we move on to question number 2. The JMPI instruction has an immediate operand. When it executes, it changes the program counter to what the immediate operand specifies. Consider the following instruction, JMPI to some label. When this instruction executes, the processor continues to execute or continues execution, bad grammar here, where some label is defined. The unconditional jump is useful to handle the case when a conditional branch does not want to branch. This is mostly because TTP lacks conditional branch that branch when the flag is cleared or when it's 0. Consider the following code. So this one, it requires a few things. Okay, the first one is to understand what is CMP, what is the compare instruction. The compare instruction, all it does is to perform a subtraction, but the subtraction is going to influence all the flags. The reason why we know that is because when we look at the circuit of the processor, let me bring that into view first. There you go. There you go. So this is inside the ALU. When we perform a subtraction, which is done by the subtractor here, the output of B, which is the borrow, is going into a multiplexer down here. Right here. So B as a tunnel goes into this particular multiplexer, and this multiplexer selects what input to connect to C out, which basically is stored as C, based on the same select pin as the operation selection. So when we have a operation selection, OPSCL, that switches the demultiplexer to the two demultiplexers to send the data to the correct calculator, so to speak, to perform the calculation. But it also selects the input from the multiplexers so that we know, whose output we should use as the actual output of the ALU. So the compare instruction does this. And as a result, okay, let me see, where's the quiz? Not this one. this one here. All right, so as a result, it's a subtraction, and the carry flag is essentially the same as the borrow flag. So we are really asking, after subtracting b from a, what does it mean whether the borrow flag is set or not? But you have to be careful because the question is asking when execution continues at label L2, not L1. So that means the JCI instruction did not branch to L1, and that's how we fall through to the JMPI L2 instruction. So in that case, that means the borrow flag is a 0, because if the borrow flag or the carry flag, because they really are the same thing. So if it is a 1, we would have branched to label L1 already. So that since we did not branch to label L1, that means the borrow flag or the carry flag is a 0. So when the carry flag is a 0, it means in a subtraction, it means the minuend is not less than the subtrahend in a unsigned interpretation. So that means all the signed interpretation can be ignored. So the first, the second, the third can all be ignored. And the confirmation is not the case that a is less than b. Since a is not less than b, it is the same as saying a is greater than or equal to b. So this particular question does require you to look into the processor circuit, especially the ALU, find out what is the carry bit, what is the significance of the carry bit in the flag, and also to remember in a binary subtraction, what does the borrow flag mean? The overall borrow flag here, what does that mean? And also to understand, how we can get to the JMPI to L2 instruction, because we would not be able to get to JMPI L2 if the carry flag was a 1, because in that case it would have continued execution at the label L1. So it does require a combination of the things that we have learned up to this point. Here's question number 3. Question number 3 is really mostly just instructions. And then the answer here, I made a mistake because I changed the processor. I added an extra output pin, and as a result, I did not change the question. So the correct answer is RIENCLK. But that's I'm not sure how I can get Canvas to regrade your submission, because I think some people might have gotten the actual correct answer, which is this one, but Canvas would have marked it wrong because the key was not using this as the answer. So if that is the case, I'm going to manually go in and give you guys back that point. All right, moving on. And this is the last one. So the last one, for the most part, is really just going through the exercise of creating the program, run it in Logisim, use the trace or the log ability to find out how many times the instruction at label. Okay, let's see what the question is asking. So we want to find out how many times the no up at label L2 has executed. So the way to do this is to put this into the assembler and then find out what is L2. So L2 is defined to be just a number, which is the address of the no op instruction right after that. So once we know that value, which is basically the address of the no op instruction, then what we do is we log the program counter, and we might also want to log OP fetch, because when OP fetch is a 1, then we can actually look at the PC, the program counter, and know for sure that that is the execution of the instruction at that place. So if you just track PC, I think in this case it will work too. So you just have to track PC and then find out how many rows has the program counter matching the address of or the value of L2. So that's how we can count the number of times the no op instruction executes. And for this question, you need to run it for all 5 variants. So you have to run it, for the first one in, I forgot to make this plural. Somebody thought that N1 would be just a singular, but that is not the case. N1 is just a placeholder, so you have to actually count the number of times that particular no-op instruction executes. So regardless of your actual student ID, the JOI instruction is going to execute 6 times, and that is the maximum. So none of these numbers can exceed 6. They can be up to 6, but they cannot exceed 6. And JOI is going to be exactly 6. If I remember correctly, JLI and JSI are going to be the same, and that's also going to be the same with JCI. So JCI, JSI, and JLI should all end up with the same number. JZI can be different, so and they don't have to add up to 6. So what you get for JZI, and when you add it to JCI, it doesn't have to add up to 6. All right, so let me see if there are any questions before I move on. All right, I am. Oh, okay, there we go. Now we got a few questions coming. That's good. All right. All right, yes, I can do it in Logisim. Okay. So let me do exactly what needs to be done here. Okay. So the first part is really just to copy and paste this code and make some changes. I'll show you what I mean by changes. Let's see, where's my assembler? There we go. Go to the source tab, and then we just go to column A, paste in the entire code, and it's going to complain a little bit because JXI actually does not exist. So let's go ahead and change this one to one of the 5 conditional branch instructions. Let's say change it to JCI. And when you change it to JCI, the assembler should recompile or reassemble, and the error message would go away. And over here, we have to change the actual ID, and it is the rightmost digit for this one. So let me change this one to reflect my ID. So my ID has 000, and then this one is a 6. This one is going to be another. Oh no, this is going to be a 6, 8, and this one's going to be another 8. So it's better to use a text editor to do all the editing. It's not like you cannot do it here, but you certainly cannot insert new lines because that will mess up the assembler for sure. All right, so my ID is 0006887, and now I'm ready to download the code. So to download the code, you go to RAM file, and here's RAM file. Make sure that the first line reads version 2.0 raw instead of reporting an error. Then you go to File, Download, and I personally just choose CSV as an extension. You don't have to do it that way, but it works out better for me this way. So I'm going to call this one jci.csv, press the Enter key, and it is now saved. So next thing to do is to bring up, oh, that's my OBS. Let me find where's my Logisim. There we go. So here's Logisim. And then what we do is we get out to the main design, and I can just do a hard reset in this case. So go ahead and reset simulation, because I'm loading in a new program, so it doesn't matter whether I'm clearing RAM or not, because it's going to get a new code in here. And this is going to be jci.csv. Press the Enter key so we can see how the content is already loaded here. So here is this is where we need to specify how we want to log the output. So we go to Simulate, go to Logging, and it will give you this particular window. PC is going to be important, so pick either one. Both PC will work. And I would, personally, I would also choose OP Fetch. But you don't need to use OP Fetch for this particular program, because for this particular program, PC alone is going to be enough, because we don't have any conditional branches right before the no op instruction that we're supposed to track. If that was the case, or if you have an LDI instruction right before the no op instruction that we are supposed to track, then you also need to get OP fetch, because otherwise it can report that it seems to be executing that no op instruction, but it may not be the case. So now we go here. I personally like base16 for the program counter, and then I will go to file. Okay, so I specify this is going to be logged in jci.tsv. So the output, I'd like to change it to TSV for tab separate the value, because if you don't, and you try to open it in the spreadsheet, it's not going to work. You can always open it in Notepad. Alright, so file output enabled, close window, and now we can start to run the code. And to run the code, we are just going to turn on the clicking. So we have ticks enabled, which is Control K, and we just have to wait until the halt pin is 1. So here's Control K, and at some point it's gonna settle. There we go. So how fast it gets to this point depends on a few factors. So let me stop the ticks first. So it depends on what is the frequency that you specify for the tick. If you specify 4.1 kilohertz, it's going to get there sooner. Since I only specify 32, it's basically running 100th. It's running at 100th of the speed of 4.1 kilohertz. So it's taking longer this time. But that's okay. And then what we will do next is to take a look at the result, which is stored in the file. So let me look for that particular terminal. Not that one, that one. There we go. So we want to look at jci.tsv, and this is what it looks like. The program counter is the first column, OP fetch is the second column, and we got some questions. Does it differ if I run the program before doing the log? Well, if you don't do the log, then it's not going to be able to show you how many times you get to a certain location. So I'm not sure whether I understood the question correctly or not. But if you don't specify what to log, you're not going to be able to tell how many times you get to a certain location. So once we have this log file, I go back to the assembler, and then we go to the assemble tab to find out how L2 is defined. So the definition of L2 is right here, and we can see that it is at location 14 in hexadecimal. Okay. Yeah, you have to specify the log before running the program in order to do the counting, because that's the only way you can do the counting. Unless you are manually doing Control T in the simulator, in which case it's going to take a long time to get this done. So at any rate, we are looking for 14 in hexadecimal in this case. That's how L2 is defined. I showed you guys how to use the symbol table to also find how a label is defined. And yes, I know this looks really ugly, but the information is there. So we are looking for L2. Gosh, yeah, this is hard to read. It's in JSON, JSON format. So here's L1, here's L3, and here's L2. So L2 does have 22 in decimal as its value. So 22 is one. It should be 16 in hexadecimal, right? Because 22 minus 16 is a 6, so it should be 16. I remember I said 14. That would be erroneous. It should be 16. So I take it back. It should be 16. L2 should be 16 in hexadecimal. So now we go back to the text file and just count the number of times 16 appears in the column of PC. And since I'm using Vim, I just use search for 16. So this counts as 1 because these these two, they are not fetch cycles. And since they're not fetch cycles, they don't really count for anything. And this is this is a fetch cycle because the second column is op fetch, so this counts as one. So the other way you can do this is to basically just do a search. There are tools to do this. So here's one, and okay, so it's hard to keep track, unless you are looking at the line number. Then you can find out, which one is which one. But that's the idea, is to really just to do the count. Since we only have to count up to 6, I don't think it's going to be a huge deal that we have to do counting this way. Now in Linux, there are a lot of useful commands that can do something like this. One is called grep. So if you use grep, you can specify the grep pattern, which is a regular expression. Remember regular expression? The way I specify the syntax of a base 10 scientific notation or the E notation. Yeah, it comes in handy even in this case, because now we can look for 1.6 and \t is a tab, because the file, remember, is tab separated. So that specifies a tab character, and then after that we need a 1 as the op fetch value. So this is the string that we are looking for. It describes the string that we're looking for, and then we have to look for it in this particular file, and it doesn't work. It is supposed to work. What did I miss? So maybe it's not this. Okay, let me. Yep, there we go. So that works. So tab is not \t. Huh. Okay, now I'm curious. Okay, how do we specify tab character in grep? I'm fairly sure it is supposed to be a \t. Control V and then tab. That's how I did it the other time. Okay. All right. So so to answer my own question, with my ID, the JCI instruction, or I shouldn't say JCI instruction. When the JCI is the JXI, we got to label L2 exactly 5 times, like that. So I'm not sure whether this answers the question or not. The other way to do this is to use a spreadsheet program to open up the TSV file, like LibreOffice JCI.tsv. And off the screen, it's asking me how to import, and I can just confirm that we are using the tab character. So once it opens, it becomes just a table like this. And once again, you can just look for 1.6 and a 1, and just have to do the counting this way. All right, so there are a few text items in the channel, and let me go through those. All right, so at 5:30, there's a question of, do we have a lab that is due tonight? I think you can assume the default is yes, we have a lab every day. There are very few occasions that we do not have a lab. So that answers that question. Next one is log in the instruction register and looking for 40 followed by 00 would also work. Generally speaking, it's not going to work, because generally speaking, if you have a 40 followed by a 00, that simply means you have an unconditional branch followed by a no-op instruction. In this code, maybe, okay, I haven't. Let me check the code first and see if it will work in this case. So go back to source. So we're looking for JMP instruction, like JMP L2 and JMP L3. L3 has an increment instruction. L2 has a no-op instruction. So in this very specific program, it does work. But in general, it may not work. So that's not a very sure way to do it. Okay, using the address is much better. And then we have the next point, which is Excel spreadsheet is also very easy for this counting. Yes. So count if will work, and that's so that particular they call it a formula in a spreadsheet will work if you do not also log opfetch, because if you turn on opfetch, then will be 3 entries, for every single address of instruction that we are executing. So that's going to be a little different. But regardless, the point is it's just a matter of counting. Okay, and what we need to log is that part is kind of asking, do you understand what is the significance of the program counter? What does it do, and how does it relate to being able to track how many times a particular instruction executes? So there's that. All right. So, any other questions about that lab? All right. If there are no questions about that lab, oh, there we go. We have something. We have text incoming. But I'm going to collapse this block so I don't have to scroll all the way down in order to find something. Alright, so for tonight's lab, can we get the weekend to do it? Why would you even ask? No. I mean, that's the whole point of having a lab time scheduled for this class. So the answer is no. We are going to do it this night, tonight, and get it done. So that way, you don't have to do it over the weekend. It was worth a shot. Not really quite sure how to respond to that, but so I'm gonna not respond to that. All right, so what we'll do today is to this is optional, okay? Because from here on we're gonna use we're gonna edit programs a lot. NVim or NeoVim is an editor that is capable of that has a lot of flexibility. That's the best way to put it. And it also has syntax highlighting, and I wrote a syntax highlight rule for the assembly language that we are using. The nice thing about using NVim combined with that syntax highlighting is as you type, it can identify static issues. So if you have a syntax issue, or if you misspell a mnemonic, or you put parentheses where it's not supposed to be, stuff like that, it will catch and be able to show you right away and go like, okay, this is not right. It doesn't catch everything, okay? There are many things that the editor is not going to be able to catch, but it does make it, I would say, with myself, okay, 80%, 90% of the mistakes that I make will be catchable using syntax highlighting. So to me, it is a efficiency boost, but for you, it may not be, okay, because NVim or Vim or VI is not an easy editor to learn, and to set it up is also not going to be super duper easy. So unless you're comfortable with reading how to install something on your computer, go through the instructions, learn how to use a new editor, and trust me, this one is not going to be intuitive, and you have the time to do it, okay, go ahead and use NVim. If you already have exposure to VI, from prior classes, then NVim is basically the same thing. So you already know how to use the editor, then it may be worthwhile to switch to NVim because of the syntax highlighting. So that part is entirely up to you. So now we go to compiling C structures, because tonight's lab is in a way the translation of C code into assembly code. So we're going to get started with compiling C control structure here. Now remember, when I say C, it really means C or C++, okay? Because in our context, it is basically the same thing. All right. So here's the module, and we'll start with control structures. There are only, let's see, 1, 2, and 3. There are 3 control structures that I'm concerned with, because the rest can sort of be done using these 3 or one of these 3, so I'm not going to be using some of the other control structures. The first one is a conditional statement, and this is a typical conditional statement where C, block 1, and block 2 are basically just placeholders. So they are placeholders for the condition, the block of code to execute if and only if the condition is true, and the block of code to execute when the condition C is false, if and only if the condition C is false. Okay, I have to be more specific. So that's a conditional statement. I am counting on you and your knowledge of CISP360 to remember how to make use of a conditional statement. So as it turns out, this code here, which is structured, and that's why CISP360 is called structured programming, because you can embed statements inside as a part of another statement. This is not structured, or not nearly as structured. So this is going to if you turn in code like this for your other classes, you probably will get dinged for points because you're not supposed to use go-tos. In many classes, many professors will just flat out say you cannot use go-to. But in this case, we are using go-to because we are trying to reduce the code that was originally structured to something that is not structured, because assembly language programming is not structured. So the translation is if C is not true, we go to label L1. Label L1 is here. And then we just continue to execute block 2, which is corresponding to the block of code to execute if and only if C is false. And then we get to L2. L2 doesn't really do anything from the context of going for the else branch. What if C is true? If C is true, then not C is going to be false. That means we are not going to go to label L1. And that also means we're going to fall through to block 1. So block 1 is here. It is the block of code to execute if and only if C is true. And after block 1, we have an unconditional go to label L2 because we don't want to fall through. Okay, at the end of execution block 1, we don't want to continue execution with block 2. So that's why we need a unconditional branch to go to L2 right after block 1 so that we don't accidentally fall through to block 2 here. Alright, so I'm just going to pause and see if you guys understand the equivalency between the original structured code and this is what I would call the flattened code because it is no longer structured, or at least it has one fewer level of structures, because block 1 and block 2 may still have nested statements, but at least I got rid of the nesting from the perspective of the original conditional statement. Alright, so I'm going to pause a little bit here and see if you guys have any questions about this slide. Alright, I am not seeing any questions, so I'm going to assume this is understood and there's no problem with this. So the next question is, what if there's no else case, right? Because else, this entire part is actually optional in a conditional statement. So if there's no else, you just have if some kind of condition C, and then you have a then block of block 1. Then it translates to really just this statement here. If condition C is false, we just go straight to label L1. If not C is false, which means C is true, then we continue execution with block 1 and there's no branching around it. So it's a simplified case. Okay, you can kind of imagine this case here, this case here is really the same as this case here, except block 2 is empty. So we can do a little bit of optimization, avoid one unconditional branch, and that's it. Otherwise, it's pretty much the same thing. Alright, still no questions. Now we move on to loops. The typical while loop in C, I call that a pre-checking loop because you check the condition before you perform the body of the loop. So in this case, C is a placeholder for the condition to stay in the loop, and then block 1 is a placeholder for what you need to do per iteration of the loop. So this code translates to this code over here. We have L1 at the very beginning because when for each iteration you have to go all the way back to evaluate condition C. But we flip the polarity of condition C, we put a negation symbol here because instead of looking for a reason to stay in the loop, we're looking for a reason to get out of the loop. So if the condition not C is true, that means we are supposed to get out of the loop. Then we have a go-to statement here to go to label L2, and L2 is basically right at the end after the looping back of the while loop. If C is true, then not C is going to be false. If not C is false, we are not going to label L2, and instead we fall through to block 1. Block 1 is the body of the loop. We perform all of those statements, and then at the end we have a unconditional branch or unconditional to go back to label L1 so that we can check condition C again to see if we have another iteration to perform. So let me pause and see if there are any questions about section 3.2. All right, I'm not seeing any questions with regarding 3.2. Then we are going to move on to section 3.3. So section 3.3 is the explanation of how to do basically the same thing, flattening the code, but this time using a personally, I think this is rare. I would say maybe 1 to 2% of the time, I might want to use a do-while loop, which is I call these post-checking loop because we perform the body of the loop first, and then we check the condition to see whether we have another iteration. So this one turns out to be easier. We have a label L1, to get back, to perform the looping. And then we have block 1 right after label L1 to mark basically the body of the loop itself. And then after block 1 is done, then we check the condition. And this is the only time when C is not negated because we are looking for a confirmation of C so that we can go back to the earlier label to perform another iteration. So that's section 3.3. Do we have any questions about section 3.3? All right, so there are no questions about that. All right. So now, I can already tell you right away that unconditional gotos, like this one here, that they translate directly to JMPI and then whatever label you want to use. So gotos are very easy to translate unless it is the then portion of a conditional statement, because then it becomes a conditional goto. So ideally speaking, we want to be able to translate conditional goto into conditional branches like JCI, JLI, JOI, JZI. But it may not be that simple because it all depends on what is the condition C. So the condition C right here, the condition C right here, right here, can be very simple, can also be very complicated. So the next question is, what if C is complicated? What if it is a conjunction of some disjunction, and then inside the disjunction there's a negation, and so on and so forth? How do we deal with all of that? So the next section kind of talks about that. So instead of we can make the code more complicated, and use that we can trade code complexity to reduce the complexity of the conditions. So the first Boolean operator that we want to talk about is the negation operator. So if you see something like this, if not C go to label L1, you can translate that into if C go to label L2, which is here, and then you have an unconditional go to L1 right after the conditional to go to L2. Because if you think about it, the only time you end up at label L1 to continue execution at label L1 is if and only if C is false. So if you look at the other code, if C is true, we just go around the unconditional branch to L1, and L2 is really just what I would call a continuation label. It's just there so that we can skip over something. So this code here and this code here are identical in terms of when we just continue executing whatever is after the original statement, and when we end up at label L1. So they both would do exactly the same thing. One looks more complicated. Okay, this version, or the transformed version, is more complicated. but it doesn't have the negation operator anymore. You can see how one relies on the negation of C, and the other one does not have a negation of C. So this is how we can trade code control structure complexity to make the condition look simpler. Okay, that's for section 4.1. Section 4.2 is asking, what if the original condition ends up is a OR? Now, C by itself can be complicated. D by itself can also be complicated. I'm not concerned about reducing C itself into very simple form or reducing D itself into very simple form, because right now my concentration is the last operation, which is an OR. So if you originally start with some code that looks like this, it will translate into something like this. In other words, I will check C by itself first. If C by itself is true, I'm just going to go to label L1. Because with an OR, if at least one side is true, we are going to the entire disjunction is true already. And if C is false, then we'll fall through to evaluate the second conditional statement. In that case, we'll evaluate D. If D is true, then we use the second chance to go to label L1. Now, if C and D are both false, then we'll continue execution right after whatever is right after the if D go to L1, which is the same behavior as the original code, because if C and D are both false, then we just continue to execute whatever is after the conditional go to on this line here. So let me see if there are any questions about how we reduce the complexity of a disjunction by complicating the control structure itself. All right, so we got some questions coming. At least one. We got at least one question coming. If C and D are true, we execute twice. Well, what do you think? Okay, so what do you think? After we get to L1, do we get back to here? Go to is just saying continuing execution at label L1. It doesn't come back. All right? This is not a call. We are not calling a subroutine. Instead, we are simply continuing execution at a label. So once we get to label L1, it doesn't know how to get back to here. D, exactly. So Curtis is correct that D would not even be evaluated if C is true to begin with. Because we are using what we call lazy evaluation or short-circuited evaluation. They should have taught that concept in CISP310 is the AND and the logical AND and the logical OR operators in C and C++ are both short-circuited. In the case of an OR, if the first or if the left-hand side of the OR is true, then it will not even bother to evaluate the right-hand side and just conclude the entire OR is true. In the case of an AND, if the left-hand side is false, then it won't even bother to evaluate the right-hand side and conclude the entire conjunction is false. So that concept should have been taught in CISP310 because it's a very crucial concept in order to make efficient loops. All right, so that brings us to conjunction or AND. So if the original condition looks like a conjunction like this, now once again, C itself can be complicated, D itself can be complicated, but right now my concern is just the AND operator connecting the C and the D. So if originally it looks like this, then it becomes something like this. If not C, we go to label L2, and once again, label L2 is a continuation label, which basically means, oh, there's no chance we're going to go to label L1. Let's just continue with whatever is after the original statement. Now, what if C is true? Well, if C is true, not C is going to be false, which means we are not continuing execution at label L2. Well, at least not right away. So that means we fall through to evaluate if D. So at this point, we know C is true already. If D is also true, then we end up at label L1 because that will satisfy this condition, which in return is going to go to continue execution at label L1, which is the same behavior as the original code here. Now, what if C is true and D is false? If C is true, then we will not continue execution at label L2, not right away. But when we evaluate the second conditional statement, D is false, so this will fail. This condition, it will fail, which means we are not continuing execution at label L1, which also means we just kind of fall through to whatever is after the second conditional statement, which is basically just continuing execution at label L2. And those are the only three logical operators that we use in C and C++. And so section 4 basically talks about how to reduce those operators by complicating the control structure itself. So we are gradually, getting to the point where we can translate the code directly into assembly code. So I'm going to pause a little bit and see if you guys have any questions about section 4. Alrighty. I'm not seeing any questions. And then we move on to section 4.4. So section 4.4 talks about simple reductions, which means sometimes, most of the time, we don't really need to perform these transformations blindly, because a lot of times we can just utilize tricks to do this. For instance, if we have a negation of x is greater than or equal to y, instead of complicating the control structure using this approach here, we can simply say, to see if to confirm that it is not the case that x is greater than or equal to y, we are really just checking whether x is less than y. So in this case, we are getting rid of the negation operation by changing the way we compare these two values. We can also look at this particular example here. If you're checking whether x is less than y or x is greater than y, it really is just checking whether x is different from y. So that's also another way to avoid the use of these methods, which complicates the control structure, by changing how we express the comparison. So that's section 4.4. And in section 5, is something that I think we have seen this already. I'm not 100% sure. So when it comes to comparison, if you remember from the binary comparison module that we talked about a few weeks ago, the only thing we can confirm is whether the minuend is less than the subtrahend after a subtraction. Okay, but that's okay. That's enough already, because once we have the ability to confirm less than, then we can also confirm greater than by reversing the two sides of the comparison operator. If you want to confirm x is less than or equal to y, then you can compare. It's equivalent to x is less than y or x equals to y. Now, equality is doable. It's doable because we have the z flag. So we'll talk about the z flag in just a little bit. Greater than or equal to, simple. We just reverse the order of x and y, and then also check for equality. Equality is easy. Inequality is also easy in this case. All right. So given the flags that we have, the C flag, okay, the three important flags that we use would be the C flag, which is the same as the borrow flag, the L flag, which is checking for less than for signed interpretation, and the Z flag. So we haven't really talked about the Z flag much. So what we'll do is, let me just check the time. Yeah, why don't we check that now? Okay, we'll look into the Z flag and see how it works. So you might say, but Tech, you don't have a module. You didn't write a module to talk about this. I don't have to, because everything is in the architecture already. So it is really important to understand, to learn how to read the schematic of the processor, because it is quote-unquote self-documenting. once you know how to navigate, understand the connections, understand the components, that is how I don't need verbal description of how the processor works. All right, so let's check out the Z flag. The Z flag is oh, I cannot remember which one, but that's okay. That's why we can look into the ALU and we look up Z out, which is the Z output. So Z out is, okay, let me just change to the poking tool so it doesn't keep warning me. So the Z flag or the Z bit output is bit 1 of the output. Okay, so now we know bit 1 of the flags register is the Z flag. Okay, so how is that going to help us? It's not. So we need to track down Z out and find out how Z out is getting its value. So this is Z out, and that's the only place where Z out is determined. So what it does is it looks at the output of the ALU, the actual result after a some kind of computation, and it uses a splitter. See this splitter here? It splits all 8 bits. Now how do I know those are 8 bits here? Because you can see how the output pin has 8 bits. So I split all 8 bits into individual bits, and we make those bits go into a NOR gate. This is a negated OR gate. So the negated OR gate will take every single bit as one of its input pins, and then we'll do the NOR on all of those bits. So if you just think about OR, okay, OR is easy to understand. If at least one bit in the input is a 1, then the output of the OR is going to be a 1. So NOR is really just the negation of that, which means if at least one input of the input pins, there are 8 in this case, if at least one is a 1, then the output is going to be a 0, which is also going to say, which is also the same as saying if the output of the NOR gate is a 1, if and only if all the inputs are zeros. All right, so if all the inputs are zeros, then the output is a 1. So that is basically saying if the Z flag is a 1, it is confirming the end result of whatever operation we specify here results in a 0 as the output. That's the Z flag. Okay, so the other way to explain this is the Z flag is a 1 if and only if the result of an operation is indeed 0. It confirms that the result is a 0. That's the Z flag. Now, technically, we don't even need a Z flag, okay, because we can confirm equality using just less than, but it really is a lot of hassle. And this type of gate logic is simple enough. It doesn't use up a lot of transistors. So most processors, have a circuitry to specifically look for equality, or the result being 0 in this case. All right. Do we have any questions up to this point? No questions? All right. So if there are no questions, we're going to translate some C code and see if we can get the hang of it. Okay. So getting back to the module, it talks about how we compare. So if you have x, r, y, and r is the relation or the comparison operator, then you basically want to translate this code into a compare instruction. Basically you have a subtraction, so that you're subtracting y from x, but you're not storing the difference. You're just going through the motion of doing the subtraction, and then this r here is representing this r over here. And we want that r to be less than, because that's the only thing we can confirm, either that or equality. So r should be a less than, or should be an equality check. Once you have r reduced to either less than or equality, then we can choose the right instruction, the right conditional branch to implement that. All right. Okay, I'm still not seeing any questions. All right. So if there are no questions, what I'm going to do is to go through an example of translating some C code into assembly code. Okay, I'm going to do a new window, and we're going to do something relatively simple. So I'm going to assume all the values that we are dealing with are in registers already. So there are 4 registers, remember, A, B, C, and D. So let's go, let's try this code here. Okay, so we are going to find the maximum of A, B, and C, store the maximum in register D. So we're only playing with registers. We are not dealing with quote-unquote variables just yet. So we can assume, at this point, we assume everything are in registers. Okay. So the code to do this is, there are several ways to do it, but I'm going to do it in a nested way, just so that I can show you what we can do with nested statements. Okay. So we say if A is less than B, then we have this block of code, else we have another block of code. So this is very typical, a typical way of how I write code. I just write out the entire structure first, and then I go back in and flesh out the content. So if A is less than B, then B or C can be the maximum, because A is already confirmed to be less than B, so we know A cannot be the maximum. In the other case, okay, we are not confirming that A is less than B, which means A is greater than or equal to B. But in either case, A or C can be the maximum in this case. All right. So now, if I know that B or C can be the maximum, then I need to compare those two and see which one is the bigger one, or just the other way around works too. So now we can say, let's compare B or C. If B is less than C, we perform some operation here. Otherwise, we perform some other operations. And then over here, we already rule out that B is may not be the maximum. So in this case, we're only comparing A versus C, so that we can differentiate which one is the maximum. So I typically just write out the entire structure first and then backfill. All right. So what does it mean at this point? Well, it means A cannot be the maximum at this point, and we also confirm that C is larger than B. So C is indeed the largest one. So D, which is where I'm supposed to store the maximum, is going to get the value of C. The other one is exactly the opposite, because if B is not less than C, that means B is at least the same amount of C. So I can assume that B is the maximum in this case. And kind of the same deal over here. C is confirmed as the maximum in this case. And now we have just confirmed that A is the maximum. So this is the C code. And now the question is, how do we translate that into assembly code? All right. So let me show you what NVim can do. Okay, because some of you may want to do this, but I'm not going to do end user support for learning how to use VI, because that really is kind of a class on its own. And I think if you are interested in computer science, this is a good way to test whether you can learn how to use a tool by yourself. You can watch tutorials there. If you just look up VI tutorial, even on YouTube, you will find plenty. And there are also plenty of tutorials that are not video based. Instead, it is written. All right. So I'm just gonna perform the coding here. Let me see how I want to do this. Okay, I'm going to do it in a interleaved way. Okay, so this is how I'm going to do it. So the first thing is I'm just copying the selected block of code into a file, which I'm going to call findmax.ttpasm. And you will see that ttpasm is not really a common extension. It stands for Text Toy Processor Assembly File, which is where we want to put the mnemonics into the file. But that's okay. It kind of works out too. So this is how I paste the content into that file, and now I can get into that file. It's called find max. There we go. And you can see right away, the syntax highlighter says, I don't recognize if, I don't recognize open curly brace, I don't recognize D equals to C, because those are all C construct. Now the comments it's okay with, because the comments are the same in syntax between TTP ASM and C++, so you can recognize that. So now we can just substitute the beginning of every single line with slash, slash, and a space character. So now all I have done up to this point is really just to comment out the entire C program. So that way I can interleave my assembly code with respect to the original C code. All right. So now we are here, and we want to compare A and B, and we want to confirm that A is indeed less than B. Once again, there are many ways to implement this program, but if you want to follow the original code as closely as possible and preserve which one is the then branch and which one is the else branch, then we want to compare BA, because in this case the first thing we translate it to is to say if A is greater than or equal to B, we want to go to the else branch. So let me see how I want to do this. So we want to go to the else branch, which is an else label, and the else branch is over here. So else is a label that we're going to define here. And the content is going to be the same, except that at the end of the then branch, which is here, we need to jump around the else branch. So over here we need a go to. Now this is still in C code, so I need to comment it out. So we want to go to a and if at the end of the then branch, and then the end if is just going to be all the way over here. It marks the end of the outer conditional statement. All right, so now I'm kind of done with the outer conditional statement. So we look at A is greater than or equal to B, and we ask, how do we confirm that? So as I kind of spell it out, right? Because it says A is greater than or equal to B. So this further translates to, oops, okay. All right, so this further translates to if A is greater than B or A equals to B, go to else. Okay, and now at this point we can perform the reduction, getting rid of the or operator here. So now we can say if A is greater than B, go to else, and if A equals to B, also go to else. Okay. And then with this one, we want to use less than and not greater than, so we can just flip the order and say if B is less than A, go to else. So now we have something that is relatively easy to translate at this point. But I'm not going to do that translation yet, because I'm going to look at this and we're going to have to do kind of the same thing. So to translate this, we are going to use exactly the same thing. So we'll say if B is greater than or equal to C, go to the else case. Now here it becomes kind of confusing, because if I just use else, it's not going to be the right label, because else is already used as the else branch of the outer conditional statement. This one is embedded, right? So the way I do this is I use the then first, which is marking this is inside the then branch of the outer conditional statement, but we want to get to the else of the embedded condition in the then branch of the outer conditional statement, because we're dealing with nesting here. So and then that further reduces to the same thing. So I'm not gonna go through the whole process. Okay, so we'll just go ahead and because it's the same thing. So if C and B are the same, also go to then else. There we go. And now we have one more conditional statement to flatten, which is this one here. Same deal, okay, because we know the template already. So this time I'm just going straight to the end result, which basically has the same pattern. So we say if C is less than A, go to. Now this is the else branch of the else branch. Okay, so the first else is indicating we're dealing with the else branch of the outermost conditional statement, and then the second else indicates we are dealing with the else branch of the nested conditional statement. Okay, so now we say if C equals to A, also go to else, and I forgot to define where the label is supposed to be, the then else. So this is where then else is supposed to be. So we have then else as a label definition to go here. And we also want to jump around from the then branch. We're supposed to jump around the else branch. So we need a go to. Oops. So we need a go to go to the end if of the embedded conditional statement of the then branch of the outer conditional statement. So this would be then and if, which is going to be right here. And this one does not need to be commented because the way we define labels are the same between C and assembly. There we go. And then we're going to do the same thing here. We need to jump around the else case. So this will be jumping to else and if. The first else indicate this is the else branch of the outermost conditional statement. The end if indicates this is the end. We're jumping to the end of the nested conditional statement inside the else branch of the outer conditional statement. So that's supposed to go here. Else and if. And we also need to define the label. So else needs to go here. All right. So now we got the labeling, and also we have reduced all the comparison to something that the assembly language can do. So now we go all the way back to the beginning of the program, and we focus on how do we do this? How do we confirm that B is less than A, and how do we confirm that A equals to B? And use conditional branch like JCI, JZI, those things to perform the branching. All right, so everything, if you want to find out whether something equals or is less than something else, you always need to use the compare instructions, CMP. So we know that we have to use CMP, and we can confirm whether the first operand is less than the second operand, which is what we need to do down here. So compare BA is what we need to do. And then the question is, what conditional branch should we use here? In other words, we have JXI to else in this case. The question is, what should be this X? So in this case, it depends on whether A, B, C, D are signed versus unsigned variables. It really makes a difference now, because if A, B, C, and D are signed, we are supposed to use JL, to check whether the minuend is less than the subtrahend. If they are unsigned, then we're supposed to use JCI. So I am going to make an assumption that those are all unsigned. So we will say uint 8 underscore t a b c d. Okay, so this is really just a notation to remind ourselves that we should interpret the values of a, b, c, and d as unsigned 8-bit integers. So if that is the case, JCI is going to branch if and only if b is less than a. And okay, so I'm gonna put these right after the equivalent C code. And this one, if we just want to confirm that they are the same, JCI would do the trick. So this template remains the same over here as well. So we want to compare C versus B. So we have CMP compare CB in this case. The first one is branch if and only if C is less than B. So it's JCI again to the label of then else. And then the next one branches if and only if C and B are the same. So JZI is going to be used in this case. And then we have another evaluation, similar type of evaluation over here. Same thing. We need to find out the ordering between register C and register A. We do a compare CA in this case. If C is less than A unsigned, we do a JCI to the label, which is else in this case. And if they are the same, we use JZI to go to the same label, which is else. So at this point, I have taken care of the control structure completely already. Oh, I missed a few things. Because these unconditional branches also need to translate to their equivalent assembly code. So all the unconditional gotos basically just translate to JMPI and using exactly the same label name. So let me just make sure that I'm not missing any one of those. So here's another unconditional goto. So we have a JMPI to then and if. And then we just did the other one here. And this should be one more. Okay, so I'm just going to look for the word go to. There are a lot, but I'm only looking for go to that is not conditional. So this one's done. This one is done. And this one is not done. Okay, so we have one more here. This is an unconditional go to else and if. So we're going to replace it with JMPI. Oops, JMPI to else and if. Oh, okay. We'll let the assembler complain and let me know. Oh, right here. So this is and if. There we go. Or I can search for that. ENIF, ENIF. Oh, there we go. So ENDIF. There we go. Well, there are cases where there are situations where you have to program in assembly language. The kernel or the innermost portion of an operating system probably has a certain percentage of code written in assembly. Alright, so the only thing we have not converted into assembly would be the assignment operations themselves. Okay, D equals C and so on. So here's the question. Okay, if I don't tell you which instruction to use, how do you find out what instruction to use when we want to copy a register C to register D? So the answer is the opcode table. So we look up the opcode table and see what is the closest instruction that can do something, at least a portion of what we want to accomplish. So we are looking for an assignment where we are just copying a register to another register. So AND is not going to do it because AND does perform a bitwise operation before it is copied. So the operation that will do just a copy without doing any calculation is this one here. See how x equals y? We are just copying register y to register x. So the mnemonic is CPR. So CPR stands for copy register. CP is copy and then R is register. So CPR is going to copy register Y to register X. So that is what we're going to do when we have all these assignment operations. So D equals C is CPR DC. Let's see, where's the other one? Right here. Oops. This is CPR DB. And then over here, we have CPR DC. And then finally over here, we have CPRDA. So, and I think I'm missing an end if for the overall, the outermost conditional statement, because there should be a go to end if here. So that label is not defined. This end if is supposed to go on. Oh, okay. I just didn't scroll all the way to the end. It is. I placed it here already from earlier. All right. So now we have this code already done, and it's time to test it. Okay. It's time to check out whether it works or not. So to check whether your code is working or not, it's usually a good idea to put a halt instruction at the very end. So this way, if you run the code inside LogicSim at full speed, when it hits the halt instruction, it will automatically pause and go like, okay, I'm done. And that makes it easier to kind of debug your code, because otherwise it will continue to go on, and then it wraps around to start from the beginning again. So it's really helpful to basically make sure that your program stops at the very end of your code. All right, so we'll save this and check out whether this program works or not. Okay. Since I'm using Linux and I'm using the command line interface most of the time, to copy and paste this code into the Google Spreadsheet, it's a little bit more troublesome than otherwise. If you use a WYSIWYG editor, you just kind of select a block and Control-C, copy, and then go to the assembler and then paste. So with me, using Linux and mostly command line tools, it's just a little bit more, just one step, more complicated. It's not a big deal. So now we paste the code into column A of the assembler, making sure that we don't have any errors. Okay, so if I did not fix the error that you guys reminded me of earlier, then the assembler would have caught it at this point and go like, hey, this label doesn't exist. Okay, and then I will have to go find, what it is supposed to be, change the spelling, and then, that would fix the problem at that point. All right, so this code is okay. We go to RAM file, and then we download the CSV. So what I'm doing right here is probably what you want to do for the coding of the inside the lab for tonight. Okay, and of course, the logic of what you're supposed to do is different from what I'm doing here. But otherwise, it's kind of the same thing. Oh, one more thing, since we have to switch to the LogicSim. Okay, so you might want to know two things. One is this operator here. So the NOT instruction is a bitwise NOT, because you're feeding all 8 bits into a 8-bit multi-bit OR gate, and then the output is also an 8-bit output. So that's how you do bitwise NOT, which is known as one's complement. And you might want to jot down the time. At 6:47-ish, TAC gave a clue of how to do the homework assignment. I mean, not homework, but the lab portion of tonight's activity. I'm not taking row tonight. So next thing is we load the code here. We first reset the processor. So we reset simulation. Go to the RAM component, go to select load image, and we want this time, what was the name again? Find max, that's it. So find max.csv, click open. We got the code here. All right, so at this point, the code is going to run, but whether it's right or not, we cannot tell, because all the registers are reset to 0. So we might want to change the registers just so that we can tell whether it is working or not. Okay, so we'll change register A, and we want to check whether this is working for unsigned interpretation. Okay, because that's the assumption that registers A, B, C, and D are all unsigned 8-bit registers. So to do that, we're going to check out 8.1 or 8A. This is 8 times 16 plus 10, okay, in unsigned interpretation. And then register B will give it like 17, and then register C will give it, oh, let's see. Let's give that one 60 in hexadecimal. Okay, so if you are looking at registers A, B, C in unsigned format, A has the maximum, B is the smallest, and C is the one in the middle. Okay, that's the ordering. If the program, for whatever reason, used the wrong flag to check whether something is less than the other one, then it's possible that it would misclassify and look at C as the maximum instead of A being the maximum, because in the case of register A, with that 8 here, the most significant bit is a 1, which means if you look at register A as a signed number, it would have been a negative value, and it would be quite negative in this case. Okay, so this is this will confirm whether we got the program working correctly or not. So we go to simulate. I'm going to change tick frequency back to 4.1 kilohertz, so this can be done as soon as possible. This is a pretty simple program. It shouldn't really take much time. And whether you zoom out to the main circuit or not is kind of up to you, because right now if I just enable ticks right here, it will get the whole thing done, and then everything is settled here. And then we can stop, we can disable ticks, and you can see how the maximum is register D, and it has the same value as register A, which means the program works correctly in this case. Now, if you want to retest this program, which is something that you might want to do with your own program for this lab, then you need to reset the processor, and to make sure to reset just the processor and not RAM, because otherwise you have to reload the content. You have to make sure the clock is a dark green. If it was a light green, then you have to click this icon once to turn the clock back into dark green. At that point, you can click this reset button, and it's just going to reset the processor, including the registers. So now I can give the registers different values. So I'm just going to give this 13, and this time I'll make B the maximum. Let's make it 90 in hexadecimal, and we'll make C the smallest. Let's just make it 02. And now we can run the program again to see whether this time it would conclude that B is the maximum and put 90 into D. So we go to simulate, we enable ticks, and it's done. We disable ticks, and you can see how it finds the correct maximum again. And obviously there's only one more case that we have to test, is when C has the maximum, and then but it's the same idea. Okay, you go to the main circuit, you make sure the clock is dark green, you click reset, and then you can proceed to change the values of the register, and you can test the whole thing again. All right, so this is it. Okay, and in your homework assignment, you are going to need to figure out how to perform certain operations. And I'll just go ahead and tell you that the opcode table is going to be helpful, because it's going to tell you what type of what each operation is doing, and the C code that is equivalent to that. So you can see how not x is x equals to tilde x, which is a bitwise not of x, which is also known as 1's complement. Okay, which is going to be handy for your homework assignment for your lab tonight. All right, so with all of that done, I'm going to release the new lab. Yes, I did yak a little more than beyond 6:50, so I'm going to give you back a few minutes. All right, so the lab is called absolute value. It does have coding, but I think this coding can be done in an hour, well, within the lab time, because the instruction of the lab is actually going to guide you through the process too. The access code is ABS, so I'm going to type that in the text channel, ABS, and I'll give you guys 5 additional minutes So it's July, what is it, 8th? Yep. And we'll make it due at 8:25 p.m. like that. And then save and publish. Alright, so that is that. I'm gonna walk off, and be back in about 10 minutes so I can grab something to eat before I start to answer questions. Alright. So I'm gonna stop streaming now, and get out of the voice